From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. I guess everyone knows you have homework due today. So if you haven't handed it in yet, hand it in at the end of the class. And I'm handing back the homework, the first assignment, with a solution sheet. And there was one that was turned in without a name, and no name, no credit. And so you might come up here after class and tell me what your name is. Whoever it is got 30 out of 30, so it's worth telling me your name. Also, on the solutions, I worked them out in Mathematica, but I tried to do it in a way that you don't need to know anything about Mathematica to understand the solution, at least the optics portion of the solution. And if you have any problems, come see me. I will also put these up on the website later today, and I'll put them up both as a Mathematica notebook and as a PDF file. I guess the other thing, I had a few students ask me about these little patterns where I was showing the Moiré patterns, looking at spherical waves and plane waves and so on. And there are, in the view graphs that are on the website, or that you had copied for you, there are some of the patterns in there. But I drew some new ones out last night, if we could look here, on using Mathematica. And I'll put these up on the website today. And so if you want to download these and print them out and play with them, you can do it. I guess I just did 3 of them, this spherical wave, a plane wave, and then this thing, I guess soon we'll be calling it a zone plate. So they'll be up on the website sometime today. In basketball, better than ever. And I also, for Dan up in Seattle, I now have heard of the Utes. What I heard was they lost to New Mexico. Anyway, I think we beat New Mexico, didn't we? Yeah. By quite a ways. Of course, the Utes had to play them in the pit, so that was, I have to admit, that's different than playing them in McHale. Anyway, last class we were talking about the interference of spherical waves, and we looked at 2 special cases, and let's just go back and look at these briefly again, and then we'll go on to new material. But one special case was where we had these 2 point sources separated at distance 2c, and we come over here some distance, and we're looking at the fringes over here. We're looking in a small region over here, and we said that what happens is that the curvature from the 2 spherical waves is nearly the same and essentially cancels out. And so what we get over here were essentially straight fringes, equally spaced, very similar as to what we got for 2 plane waves. So that was special case number 1. Now special case number 2 is we're going to take these 2 point sources, now we're going to look up here. And so let's look at that. So we had these 2 point sources, we looked up here, and this is where we got the circular fringes. And first off, I mean, without doing any math at all, we know that they must be circular fringes just because of symmetry here. And the other thing we know without any math is that in the center, well, the 2 beams are parallel right along this axis. And so in the center here, where the 2 beams are, this region here, where they're nearly parallel, the fringes are going to be very widely spaced. And as we move out here, the angle between the 2 interfering beams will get larger. And so the fringes are going to get closer together. And so we get these fringes like this, circular and widely spaced in the middle, and then as we move out, they get closer and closer together. And in fact, I guess we saw here that the spatial frequency increases in a linear fashion with distance as we go out here. And the radius went as the square root of integers also. One other thing I might say here, if any of you do download these from the website, when you look at the little thumbnail in the PDF file, you're going to see some strange effects. And I'll give a prize, a very small prize I might say, but a prize to the first person who either stops in to tell me what that strange effect is, or sends me an email explaining it. Okay, so that was interfering two spherical waves. And we had already talked about the interference of two plane waves. And so the next thing we want to do is to talk about the interference of a plane wave and a spherical wave. And so this takes us to section 4.3. So it's interference of plane wave and spherical wave. So let's just pick our axis here. X. And I guess I put X, but it should be Z here. And no, I keep with my notes, I'll keep it X, I guess, which is what I had in my notes for some reason. And I'll come back here is my spherical wave. And it's a distance x naught away from the observation plane. And we're going to bring in a plane wave here. For the heck of it, I'll change color. And we're going to bring in here a plane wave at an angle of theta. And so for the plane wave, we can write here k dot r is 2 pi over lambda times x cosine theta plus y sine theta. Okay? So that's the OPD across this plane. And for a spherical wave, we just say KR is 2 pi divided by the wavelength times the square root of x minus x naught squared plus y squared plus z squared. So that will be the OPD for the phase actually here for the two for the plane wave and the spherical wave. Now what we want to determine here is the shape of the fringes, and the shape of the fringes then will depend upon the phase difference between the two interfering beams. And so we simply have to calculate this thing that I've been calling alpha, which is the phase difference between the two beams. And so we can write here, therefore, alpha will be 2 pi over lambda times, I'll put the plane wave first, x cosine theta plus y sine theta. And then we will subtract the spherical wave, so minus square root x minus x naught squared plus y squared plus z squared. And might have some initial phase here, phi 1 minus phi 2. Well, what we want to do now is to, well, make life as simple as possible. So we'll say, let's pick the coordinate system. So x is equal to 0. And also let phi 1 minus phi 2 equal 0. And, I mean, there's no reason why we can't pick the coordinate system. So x is equal to 0. And the only effect of phi 1 minus phi 2 not being equal to 0 would be a shift in the fringes. It's not going to change the shape. Just shift them. And so we'd have here the alpha is 2 pi over lambda y sine theta minus the square root x naught squared plus y squared plus z squared. And this is exact, which gives you a warning that probably the next thing I'm going to do is to make an approximation or something here. So it won't be exact. But right now this is exact. And so this is the equation here. If we set this equal to a constant, and if we set this equal to an integer times 2 pi, this would describe the shape of the fringes, the equation giving the shape of the fringes. Okay, so now what we're going to do is, coming back to this equation, this drawing here, we're going to pick a region here so dimensions in this plane are small compared to the distance from the plane to the point source. In other words, what we're going to do here is we're going to say let x, the magnitude of x, naught here, the distance from the point source to the screen, will be much, much greater than y or z. So the distance from the source to the plane is small compared to dimensions in the observation plane. And so the next thing we'll do then will be to, well, we're going to expand this in a binomial expansion here. And so the largest number inside here by far is x naught. So we will first rewrite that alpha is 2 pi over lambda y sine theta. And we'll first just factor out x naught. So x naught times 1 plus y squared plus z squared over x naught squared. And then we will expand this and get then that alpha is approximately equal to 2 pi divided by the wavelength times y sine theta minus x naught minus quantity y squared plus z squared over 2 x naught. Okay. So this is an approximation that we made last class. We're going to make it almost every class this semester, many classes anyway. And we're approximating then a spherical wave by this parabolic wavefront. Okay. So let's see. So what we're doing is we're approximating spherical wave as parabolic wave. And we'll do that many times this semester. Okay, if this is going to be describing the shape of a bright fringe, then we would set this equal to some integer times 2 pi, and that would be for bright fringes. So integer times 2 pi for bright fringes. And this would be the equation describing the shape of these fringes. Now there's a kind of an interesting case here that we'll pick out. the interesting case that we're going to look at is theta is equal to 0. So we're going to go back here and bring in the plane wave along the x-axis. And if we bring in a plane wave along the x-axis, without any math at all, we can say the shape of the fringes must be, well, it must be circular. Just because of symmetry, they're going to be circular. And we could probably guess a lot more about it, but right now let's just write down the equations and see what it comes out. If that's the case, then for a bright fringe, we would have that, what, x naught plus y squared plus z squared over 2 x naught is equal to, I'll say m prime times 2 pi. Just that we have changed the sign here. It's the only thing we've done, getting to that point. And then we could also, what I have done here, I went up here. This was a minus sign, so this goes away. This is a minus and this is a minus, and m. I just changed it to m prime to change the sign of it. Okay, the question is, should that be lambda here? What we've done up here, we multiplied by 2 pi over lambda. And so this has to be equal to m times 2 pi. And so when we come down here, oh, I see what you're saying. Yes, thank you. And we have 2 pi over lambda here. I was checking to see if you're awake this morning. You're more awake than I am. That should be m prime times lambda. Makes the units look a little bit better, doesn't it? And, or what we could write here, I mean, x naught is just a constant, and so now we would have that y squared plus z squared over 2x naught is equal to m double prime times lambda. And just like we did last class, we could say let r squared equal to y squared plus z squared. And so we would have here that r is equal to the square root of 2x naught m prime lambda. And so this is the same result that we had last class when we interfered 2 spherical waves. Question?
I don't know how you threw off the x naught. And I see how you changed the m to an m double prime with this.
Well, what I did, the question is, how did I throw out this x naught? X naught is just a constant. And so I'm going to put that x naught into the m prime lambda. Now, and I'm going to call that, instead of m prime, I'm going to call it m double prime. Now, m double prime may not be an integer, because x naught is not necessarily an integer number of wavelengths. So m double prime is a number, not necessarily an integer, depending on what x naught is. Another question?
Isn't m double prime a negative number?
I could, yeah, you're worried about this up here. I can just, I could have made this a number, a negative number here, and then when I multiplied by the minus sign, it could become a positive number. So I'm not going to take the square root of a negative number for sure.
Where does the root come from?
Where does the root, okay, where does the root come from here? We're saying that r squared is y squared plus z squared. And so I just put in r squared here and solve for r. Yeah, it's not r squared, it's r. So this is the radius of the fringes. And You know, m prime is not necessarily an integer, but in going from one fringe to the next fringe, m prime will change by 1. M double prime should be. Thank you. People are awake this morning. So m double prime is just some number, but the important thing is that it's a number that changes by 1 and going from one fringe to the next fringe. And okay, the question is what, hard to read this, it's 2x naught m double prime times the wavelength. And so this is of the same form as what we had last week when we looked at the interference of two spherical waves head-on. And again, we get these same shaped fringes that we have here. Circular fringes, widely spaced in the middle, and get closer as you go out. And the frequency, again, is going to increase in a linear fashion with distance. And so interfering a plane wave head-on with a spherical wave gave the same results as when we interfered two spherical waves in this condition right here. And that should not be too surprising because you can just think of that plane wave as being a spherical wave where this point has gone to infinity. And so it's not too surprising that we still get the same shaped fringes. Any more questions? I have all my m's and m primes and then double primes right. Okay, so now you're all experts on interfering two plane waves, two spherical waves, and a plane wave and a spherical wave. So what's left? Well, a lot actually, but one thing that's left we're going to look at is interfering a plane wave and a cylinder wave. And so this is section 4.4. Okay. And so for the cylinder, what we're going to have is that Kr, 2 pi over lambda again, times the square root of x minus x naught squared plus y squared. So, I mean, it's like a cylinder, and we will have no dependence on z in this case. So it's the same as what we had before when we had spherical, except no z dependence. Okay, and so we could just go back to the same equations that we had, and let's say for a bright fringe, we would have that y squared over 2x naught is equal to m double prime times lambda. So it's just what we had before, except the z goes away. And so what we have here is what we call a one-dimensional zone plate. We'll talk a lot more about zone plates later, but and see why we call it a zone plate. But the fringes in this case would look like this here. So it's a cylinder wave, so the fringes are going to be straight in the one direction. And going this way, they change in the same way that we had for the circular fringes. Namely, one thing is that the frequency here will increase linear with distance as we go out here. So that's a one-dimensional zone plate, interfering a cylinder wave and a plane wave. And the plane wave is on axis. Any questions? If we were to tilt the plane wave, essentially what we would be doing would be picking a different portion of this zone plate. Maybe you wouldn't see the center portion, but you'd be picking a portion out here. Okay, I seem to have another pattern here in my notes, but I have no equations to go with this pattern. So let's see if you can help me understand what this pattern might have come from. So here I interfered a couple of waves again, and I got this pattern here. Can anyone tell me what I might have interfered?
Spherical wave, not cylindrical wave.
Yeah, so one could be, well, there are a few choices here. One choice would be a plane wave and another wave that had a different radius of curvature in two directions. Or another choice, as someone said, might be a spherical wave and a cylinder wave. So I have a different radius of curvature in the two orthogonal directions. Okay. Well, that's everything I wanted to say about basic two-beam interference, talking about the basic shapes of the fringes anyway. But it brings up a question I would have for you. And the question is, we haven't really gotten much into interferometry, but you probably have read about interferometers, studied them some in the past. And the question is, how many interferometers are there in the world? As you go through the books, it seems like everyone has named an interferometer after himself. So there's a lot of them out there. And I don't know what the number is, but certainly there's a lot of them. But if you look at all these different interferometers, you'll see that they really just fall into two categories. And these two categories depend really on how we combine the two beams. And so I have a short section here talking about methods of beam division. So this is 4.5. And 4.5 is going to be divided into two sections, 4.5.1, which is going to be called division of wavefront. And then there's going to be 4.5.2, which is going to be division of amplitude. And so these are going to be two ways of combining the beams. And while you look in the literature and you find these hundreds or thousands of interferometers, they're all based on these two principles. And once you understand what we mean by division of wavefront and what we mean by division of amplitude, you can look at any of these complicated interferometers and say, that's nothing but just like two pinholes, Young's two pinhole experiment, or you can say, that's nothing but, variation of the Michelson interferometer or something. So let's see what we mean here by division of wavefront and division of amplitude. And for this, I'm going to use the some of the view graphs, and I don't know if I didn't tell you to bring view graphs, so you may not have them here, but you can follow what I'm doing here and then go back and look at your view graphs if you want. The first is division of wavefront, and the simplest way of thinking about that is something where we call this Young's two pinholes. But the idea, we have a source here, okay? Don't know what the source is, but a source. The wavefront propagates along, and we're going to put a little pinhole up here and pick off a portion of the wavefront up there. And then I'm going to put a little pinhole down here and pick off a portion of the wavefront down here. And so this is division of wavefront, picking part of the wavefront here, part of the wavefront here, and then by some magic I'm going to combine this beam with this beam. And there are a million ways that you can combine these two beams. For this example here, we're combining them by using diffraction. If we make this pinhole small enough, the light's going to be spread out, and we come over here someplace, and these two beams will overlap, and we'll get interference fringes. And it's just like interfering beams, two spherical waves. One spherical wave coming from here, one spherical wave coming from there. So this is division of wavefront. Wavefront comes along, we pick off a portion here and a portion there. Okay. There are a lot of ways of getting division of wavefront. And the next one here is what's called Lloyd's mirrors, or Lloyd's mirror, I should say, because there's only one mirror here. And the idea here is we have a point source there, and the light goes out here, okay? So part of the wavefront comes here. Now part of the wavefront comes down here and reflects off this mirror. And so if I were to put my eye here and look back, I see a point source there, and I see another point source down here. Light that's reflected off the mirror. And so it looks like I have interference of two spherical waves here. Okay? So again, this is division of wavefront. Part of the wavefront comes straight through here. Part of the wavefront comes down here and up here. Any questions why we call that division of wavefront? So again, this is in the view graphs that probably many of you have. So this is Lloyd's mirror. Well, Fresnel came along. Twice the budget, he had two mirrors. So now we have the light coming along here, and I don't show it, but we really are going to block the light going straight through. Light doesn't go straight through there. Part of the light is reflected off this mirror. Part of the wavefront is reflected off this mirror. Again, if I put my eye up here and look back, I see 2 point sources. Division of wavefront again. Same thing, you know, different name, 2 mirrors instead of 1 mirror, but it's still division of wavefront. We end up with the interference of 2 spherical waves. Okay. Keep going. Fresnel not only had mirrors, he had prisms. Another example, division of wavefront. A source here. Part of the wavefront comes up here, goes through this portion of the prism. Part of the wavefront comes down here, goes through this portion of the prism. When I sit back here and look back, it's going to look like I have 2 sources, S1 and S2. Again, interference of 2 spherical waves. And again, division of wavefront. Pick off portion of the wavefront here, portion of the wavefront there, combine the 2, get interference fringes here. Okay. Well, that's examples of division of wavefront, and we could go on all day with 100 or more examples of that. But let's go down here and talk about division of amplitude. What do we mean with this? Well, here we're going to use a little beam splitter. We have a beam coming along, hits this beam splitter. Part of the light reflects up here, and then a mirror here reflects it back down here. Part of the light goes through the beam splitter to a mirror here, back here, reflects off the beam splitter, and out here. And here we have 2 beams interfering. If we tilt the mirror, say this is a collimated beam, we could tilt this so the 2 beams coming out leave at different angles. And that would be interference of 2 plane waves at an angle. Division of amplitude. Part of the amplitude went this path, and part of the amplitude went this path. So that's the difference between division of wavefront and division of amplitude. Okay. Again, if you look in the literature, you can find hundreds of interferometers based on this division of amplitude thing. Let's look at a couple more. Well, one way to divide the amplitude is a diffraction grating. So light comes in, part of the light will go straight through, and then part of the light will leave at some angle. So we have, again, division of amplitude. This time we're using diffraction We'll talk a lot more about diffraction gratings in this course. Another way of getting division of amplitude. We'll look in some more books and find more ways. Here's a couple here. There's all kinds of polarization techniques for division of amplitude. In this case, it's really division of amplitude and division of wavefront. Because if we think here, like in this plate, called a Savart plate, light comes in, one polarization is going to go in one direction, and the other polarization is going to go in the other direction. And so that's like division of amplitude. But then if we think of this beam coming straight through, and when we actually look at the interference over here, we're interfering light that was down here, portion of the wavefront, with light that goes straight through here, this portion of the wavefront. So this is really division of amplitude and division of wavefront. And you can do this both with a lateral displacement, and then there are all kinds of polarization devices out there where you do the same thing, but in an angular direction instead of lateral. One last one here. Is a very simple one, widely used, just a piece of glass. In this case, we'll say it's the two surfaces are parallel and flat. So we have plane parallel plate. Light comes in, part of the light's reflected here, so division of amplitude. Part of the light's going to go through. After reflecting off a second surface, will come out down here, and it's going to interfere with a beam that came here, down here. So we have both, again, we have both division of amplitude and division of wavefront. Okay. So there are a lot of different ways of building an interferometer, and maybe in this course I'll have you all invent your own interferometer, name it after yourself. But I warn you, it's hard to find one that's not pretty similar to one that's named after someone else already, but we can try. But the whole idea, you know, division of wavefront, division of amplitude, you throw in some mirrors, some prisms, some lenses or something, and you have a new interferometer. But that's the basic idea. Okay, that's everything I wanted to cover in Chapter 4. So you're all experts now on basic interference. Well, the interesting thing is that sometimes you combine these beams and you calculate the shape of the fringes, and you go look for the fringes, and they don't exist. You can't find them. And so the question is, why is that? And perhaps the reason is that the beams are not coherent with respect to one another. So we have to go on here and talk about what we mean by coherent. So this is Chapter 5. Again, it's one of my favorite chapters there. And it's going to be concepts of coherence. So first we're going to go through and define a couple of simple things, kind of rule of thumbs for coherence time and coherence length. And then we're going to go through and do partial coherence, talk about the visibility of the fringes, where are the fringes located, and so on. So it's kind of an interesting chapter. The references for this, I think you start off with Heck's book, because as I said the first class, what Heck did was to take portions of Born and Wolf and rewrite it in a way that people can actually understand it. But Born and Wolf is really a superb text on coherence. And so once we learn what's in Heck, then we want to go back and look at Born and Wolf, because there's a lot of very good material there. Well, the problem we come into here, why we have to talk about coherence, is that there are really two things that bother us. First off, in interferometry, first off, the thing is that light is never completely monochromatic. So let's write that down here. Light can never be strictly monochromatic. There's always some spread of wavelengths present. And the other thing is that, you know, a real source is never a point source. A real source is never a perfect point source. And so this really leads us into coherence. And when we talk about the effects that the light is not strictly a single wavelength, we'll be talking about temporal coherence. And when we're talking about the effects due to the source not being a perfect point source, we're talking about spatial coherence. Okay? So temporal coherence and spatial coherence. Well, the first thing we do is we're going to talk about something here called the coherence time. And so coherence time. And this is going to be related to temporal coherence. And what it is basically going to be kind of a rule of thumb. So it's not going to be very rigorous. Later we'll see how to make it rigorous, but it's a kind of rule of thumb that works out pretty well, actually. And the problem here, again, as we said, is that light is never strictly monochromatic. And we could write down here that the electric field, and I won't worry about polarization right now, is some amplitude times a cosine of kx minus 2 pi nu t. So kx minus omega t. And the problem here is that nu takes on several values. And so if we set up an instrument, say an interferometer, where the light is going through the two paths of the interferometer, it takes some time for the light to go the two paths, and there will be some difference in time. Unless the paths are exactly matched, there will be some difference in transit time for the two paths. And so if we come back, I'll leave that in the field here, I guess. Come back here. The problem we get into is that there's 2 pi times, let's say, the average frequency times the transit time difference for the two paths of the interferometer minus 2 pi times nu average plus some change or some spread in frequency times delta t. The problem is that if we have a path difference for the two arms, you know, delta t is some value, and because of the different frequencies will get out of step as they go the two paths of the interferometer. And what we're going to say is we want delta t, so if delta t is the transit time difference for the two paths of the interferometer, let's say delta t is transit time difference for two paths of the interferometer. We want this quantity here to be less than, and we could argue what we want it to be less than. Do you want it to be less than pi over 2? Do you want it to be less than pi? Or most books will say we want this to be less than 2 pi. As I said, this is just a rule of thumb we're going through, not real exact. So we say that we want the transit time difference for the two paths of the interferometer to be small enough that this quantity here is less than 2 pi. And so that says that delta nu, delta t, is less than 1. Okay? And so that's saying that delta t, the transit time difference for the two paths of the interferometer, is less than 1 over the frequency spread that we have. And this thing right here is what we called the coherence time. So delta t is equal to 1 over delta nu, is called the coherence time. Okay. So it's kind of a fuzzy thing, you know, I don't know, should I have made that 2 pi or whatever, you know, and it probably, the real delta t that you can have probably depends on just what the distribution of the source is, whether it's a square wave distribution or Gaussian or whatever. So this is not a very exact expression, but I tell you, it's amazing how this little simple expression, how well it will work in coming up in designing an instrument and knowing what the transit time difference can be. So that's coherence time. Now, the next thing we have here is called coherence length. And coherence length is just simply going to be how far the light travels in the coherence time. So, say, this is what, section 5.2, and it's called coherence length. And so all we do is that coherence length, L sub c, is on the order of the speed of light, c, times the coherence time. Okay? And so if we think here for a second, you know, we have some source, and we have some interferometer. I don't know what the interferometer is, but it doesn't matter. We have light, you know, going off here some path, and going off here some other path. And we're saying that if SP, this distance, minus SQ is less than the coherence length, C times tau sub C. I should come back here, and when I wrote down coherence length, I probably should have put a C here. So that's the coherence time. If this path minus this path is less than the coherence length, we're saying that the light at P is coherent with respect to the light at Q. Okay? And so we have here the coherence length is C over delta nu. Coherence time was 1 over delta nu. And if you play here for a second, you know that C velocity is wavelength times frequency. We could play with that for a second, which I'll let you do. And that will end up being that the coherence length is lambda squared average value over delta lambda, the spread in wavelength. So coherence length is C over delta nu, or lambda squared over delta lambda. Simple equation, not very rigorous, extremely useful. There aren't many equations that you should memorize, but maybe this is one. But, I don't know if you'll, depending what your work is, you'll use it so often you'll dream about it. How many of you dreamed about fringes last night? Boy, am I failing in this course, I don't know. I'll keep working on it here. I look out here and I see those shirts with stripes on them. What do I see? I see the interference fringes. Right? Okay. Well, this is, simple rule of thumb, works pretty well. What we want to do now is to go on and begin looking at this in a little more detail. And we'll look at theory of partial coherence is where we're headed here. So really, in real life, probably what we have the electric field at P and electric field at Q, and they're somewhat correlated, but probably often, the extremes of being completely correlated or completely uncorrelated don't exist too often. Generally, there's some partial degree of correlation or partial degree of coherence between these points. And so that takes us to section 5.3, which is going to start the theory of partial coherence. Maybe I'll change color here. And so basically, we have some source here, and it may be a point source or it may be an extended source, I don't know. And the light will go along here someplace, and I'll pick off maybe like the Young's two pinholes that we looked at a while ago. I'll put a small pinhole here and a small pinhole there, and in some way I'm going to combine the two beams, maybe diffraction or maybe prisms or mirrors or something here, and a point P. And it's going to turn out that by looking at the contrast of these fringes, I can determine the coherence between the electric field at this point, so E1 of T, with the electric field down here, E2 of T. So the important thing here is really going to be fringe visibility. So let's go ahead here, and what we're going to end up doing is going through few equations here and making some definitions, and then finally we'll get to where we can precisely calculate the coherence between these two fields. So first I want to look at fringe visibility. And I want to keep, I don't want to have to worry about the polarization, so I'm going to look at scalar fields. And I'm going to write down here that the irradiance is some time average of whatever the electric field is squared. And so I could write that as E1 plus E2 times a complex conjugate of E1 plus E2. So I'm combining these two electric fields here, and how I combine them doesn't really matter, but I'm combining them some way. And so I'll just multiply this out here, and we're going to do a time average of the one field squared plus the second field squared plus E1, E2 complex conjugate plus E1 complex conjugate E2. And this first guy, I typically would call that, well, we'll just write down here I1, where I1 is E1 squared average. And then I'm going to have an I2. And I2 is E2 squared. So that's fine. But then I get this other thing here that's going to be a little more trouble for me. E1, E2 complex conjugate plus E1 complex conjugate E2. And I will rewrite that as I1 plus I2. And I could rewrite this sum here as just 2 times the real part of E1, E2 complex conjugate. So I have this expression here. I1 plus I2 plus 2 times the real part of the time average of E1, E2 complex conjugate. Well, I'm going to have to worry about this 2 times real part of E1, E2 complex conjugate. And if I first say we have a coherent wave, then we've already seen here that E1, E2 complex conjugate was the square root of I1, I2 cosine, or whatever the phase difference was between the two beams. Because when we had before when we were looking at coherent beams, we just had the irradiance was I1 plus I2 plus 2 times square root of I1, I2 cosine of phi 1 minus phi 2. And so we would just write down here that, I'll write it down. Okay? And then we said that the visibility here, for this case, V was the visibility, and we said that was what, I max minus I min divided by what, I max plus I min. And we had from previous class then, I mean, we can calculate it pretty easily, that that's simply 2 square root of I1, I2 over I1 plus I2. So that's a case that we've had before for coherent light. And what we're going to have to worry about now is what if it's not perfectly coherent. So I'll take a little coffee here, get ready to go through some definitions and before we do some calculations here. Okay, so let's begin here. That takes us to 5.3.2, which is going to be called the mutual coherence function. And so what we're going back here, we're no longer assuming that they're perfectly coherent. So we have I as I1 plus I2 plus 2 times the real part of E1, E2 complex conjugate. And so, you know, as we kind of sketched before, we said we have some source here. Don't know anything about the source right now. The light's leaving the source, and then some combination of mirrors and prisms and lenses and whatever. We're going to combine the two beams. And we're going to combine 2 beams from here. And I'll just put in 2 pinholes and say, just like we had on the previous drawing here, that you know, this is E1 of t, and this is E2 of t, and this is some point P. So the thing is that light can leave this source, and it can go along 2 different paths. It can go along path 1, and it can go along path 2. And if we go along path 1, let's say the transit time is t, some number. And we go along path 2, and now the transit time is t plus tau, some different amount of time. And so I'm going to rewrite this expression down here, simply saying that the irradiance at point P is I1 plus I2 plus 2 times the real part of E1 times T, E2 complex conjugate T plus tau. So I just want to show in this expression that the two electric fields had different transit time in getting from here to here. Well, now we need to make some definitions. So when we look at the books, we know what they're referring to in the books. And so let's define this thing here. I'm going to call it capital gamma 1, 2 of tau. And I'm just going to say that that's equal to this here. So that's equal to time average of E1 of t, E2 complex conjugate of t plus tau. Okay, so that's gamma 1, 2 of tau. And we will call that the mutual coherence function. Or sometimes you see it called just the correlation function of these two fields, E1 and E2. So, or correlation function of two fields, E1 and E2. Okay? So that's going to be our coherence function. And the 1 and the 2 are meaning they're going along different paths here. And really that they're different locations in space here. And the t and the tau means it's a different path difference, different transit time difference. And another definition maybe we should make is gamma 1, 1 of tau. And that's going to be called the self-coherence function. And if we were to put in here gamma 1, 1 of 0, then that would just be I1. So the tau goes away, and the 1 is the 2. And so we have E1, E1 complex conjugate, so that's I1. Likewise, gamma 2, 2 of 0 is I2. And there are other similar definitions you see in the books, but that's probably the most important way of doing this. Okay. So who do we play in basketball this week? Washington and Washington State. Are we going to win? I get nervous. We beat Stanford and then we relax. I don't know. .3.3. So actually I'm supposed to be in, I forget the date now. Anyway, the day of the Final Four game, I'm supposed to be in Bozeman, Montana on business. And I've already bought tickets and I've paid for them. Now I'm wondering, did I make a mistake? I doubt it. But anyway, we'll see. Last year, on the day of the Final Four, I'd planned a trip to Sweden. So my wife and son and I were in Sweden. My son was convinced I had ruined his entire life because he was missing the basketball game. So Anyway, this coherence function is very useful. The problem with it right now is that it depends on the correlation between electric fields, but it also depends on the strength of the electric fields. So it depends upon the intensity or radiance. And so what we'd like to do here, what we normally do is we work with something called the normalized coherence function. And we'll call this little gamma 1/2 of tau. And that's going to be equal to capital gamma 1/2 of tau divided by square root capital gamma 1/1 of 0, capital gamma 2/2 of 0, or in other words, this capital gamma 1/2 of tau divided by the square root of I1, I2. So this is a normalized coherence function, gamma 1/2 of tau, and sometimes we call this the complex degree of coherence. And in a little while, it'll become obvious to you why that's true. Okay, so now what we can write, we can go back to our expression for the irradiance. I1 plus I2 plus 2 times the square root of I1, I2 times the real part of gamma 1/2 of tau. Okay, so we can rewrite that in terms of the complex degree of coherence or normalized coherence function. And if, let's say, I1 is equal to I2, we could write this that I is 2I1, 1 plus the real part, gamma 1/2 of tau. Okay. Well, if we think here for a second, I mean, our goal here is going to be to determine gamma 1/2 of tau. And right now, well, what do we know about gamma 1/2 of tau? We simply know that it's a complex number. So I can rewrite this as a magnitude, gamma 1/2 of tau, times e to the I phase 1/2 of tau. Okay, so I'm rewriting this complex number as a magnitude e to the I phase. Now, to be consistent with the books, I'm going to say let the phase of this guy, phi 1/2 of tau, be equal to alpha 1/2 of tau. You think I'm crazy to do this, but it's going to work out. Give me time. Minus omega bar times tau. And so this last quantity here, omega bar times tau, you can really think of as 2 pi divided by whatever the average wavelength is, times whatever the transit distance difference is, R1 minus R2. So this is going to be a phase term that really just comes out from the normal propagation of the light. And this here is some way going to be related to the source. The spectral distribution of the source, the size of the source, or something. We'll find out. So what I can do here is I can write that the real part of gamma 1/2 of tau is equal to the magnitude gamma 1, 2 of tau times the cosine alpha 1, 2 of tau minus omega average times tau. Okay. And so I can then rewrite this at I. Rewrite the irradiance. I is I1 plus I2 plus 2 times square root of I1, I2. Magnitude, gamma 1, 2 of tau. Cosine of this alpha 1, 2 of tau minus omega bar times tau. And I'll simplify this slightly, that I'll say I1 is equal to I2. And so we end up with the irradiance here is 2I1 times 1 plus magnitude gamma 1, 2 of tau cosine alpha 1, 2 of tau minus omega bar times tau. And I'll draw a box around that. And so this would be our expression for the irradiance. And so we could write here that gamma 1, 2 of tau is called the degree of coherence. And if gamma 1, 2 of tau equal 1, well, let's say we have complete coherence. If gamma 1, 2 of tau greater than 0, less than 1, we have partial coherence. And gamma 1, 2 of tau equals 0, complete incoherence. Okay. And so if we go back here and look at these two equations here, let's first look at this one here. And I were to say to you, what's the fringe visibility going here? We know it's Imax minus Imin over Imax plus Imin. And so we could write that as, well, normally if gamma were equal to 1, we would have this as a 2 square root of I1, I2 over I1 plus I2. And now we have this other term in here, gamma 1, 2 of tau. So the visibility of the fringes could be written as our normal visibility times this coherence function, magnitude of gamma 1, 2 of tau. And so if two interfering beams have the same irradiance, the visibility function here is simply equal to the coherence function, gamma 1, 2 of tau. Well, anyway, my time is up, so we'll come back to this next class and then go on from here to use this to calculate coherence functions. So I'll see you on Thursday.